So go ahead.
Thank you. Thank you very much. I am very pleased to take part of this conference. I apologize for not being there and not even connecting yesterday and the day before, because since I was not there, I was involved in other commitment in France in some other national meeting, so I was not able to connect. But I'm very glad I listened to the conference today, and I'm very glad to be part of it. So I thank the organizers for this conference and for inviting me. And I am going to talk this afternoon about experimental work and about understanding the mechanism of ultra-fast CC double bond photoisomerization in the context of molecular motors and photoswitches. And so this scientific context is the motivation for us to develop a new experimental setup that I'm going to describe in the second part of my talk about 2D electronic spectroscopy of vibrational motions inside these molecules. So this work is actually done by my PhD student, Robin Piron, who should defend his thesis in 2 weeks from now. And here are the people who have been involved in my institute, Institut de Physique et Chimie des Matériaux de Strasbourg. So the people involved in this work over the past few years or even past few weeks. This is a new PhD student starting only now. And this work is actually a part of a multidisciplinary research effort, which involves other experimentalists from the group of Giulio Cerullo, Politecnico Milano in Italy. It involves also synthetic chemists, Marco Paolino, or people from the group of Feringa, Ben Feringa, so in Italy and in the Netherlands. And it also involves several computational chemists, the group of Massimo Livucci from the United States, Etienne Guindensperger from Université de Strasbourg as well, and Mike Filatoff, who is a co-organizer of this conference. So, if I may go to the next slide, I don't know what. Yes, okay. So here is a prototypical example of a rotary molecular motor. This molecule exploits CC double bond isomerization to convert light energy into mechanical energy at the molecular scale. So it is a 4-stroke motor, so it can undergo a full rotation by 1 full turn of this rotor with respect to the stator in 4 steps. The first step is photoisomerization. So you may understand this photoreaction by plotting this simplistic representation of potential energy surfaces. You excite the molecule with 1 photon, and through a conical intersection, it decays to the ground state, possibly forming this photoproduct. So here at the conical intersection, there is a branching between molecule which will go back to the reactant or molecule which would indeed form the photoproduct. And then after, so this primary photoproduct has actually an opposite helix chirality. And so you need, as a next step, step 2, a thermal helix inversion to reset the molecule in a conformation where after absorbing the next photon, it would rotate in the same direction. And this thermal helix inversion occurs through an energy barrier, and it may take some time at ambient temperature. So if you think of how to optimize or improve the efficiency of such a molecular machine, then you would like to ideally have a high photoisomerization quantum yield, because you don't want to have the motor require too many photon absorptions before it has a chance to really make the first half turn. And then you would like to have, so typically there are different, of course, motors which perform differently, but typical photoisomerization quantum yield is in the range of a few percent of less or less. And then during step two, you would like to have a low energy barrier to avoid and not have the motor stuck here for seconds or minutes, as was the case in the first generation of motors. Okay, so actually the point I would like to underline here is that there is actually no rational strategy to optimize by chemical design either the photoisomerization quantum yield or the energy barrier in the ground state. So this is still done on the basis of trial and error. Instead, if you look at natural proteins and natural sensory proteins, some of them are triggered by a very efficient and very fast CC double bond isomerization. So you heard yesterday about this rhodopsin protein in the talk of Massimo Liucci. It has been studied for decades now, experimentally and theoretically, and it has been observed that the photoreaction, if you promote the population from the ground state to the first excited state, the photoreaction is vibrationally coherent, meaning that the wave packet that may be produced there by a femtosecond laser pulse is propagated coherently by the potential energy surface through the conical intersection and until the formation of the photoproduct. Okay, so this photoreaction has been very well studied. It is known now that there are essentially three vibrational modes, which are the CC double bond torsion, the hydrogen out of plane motion, and the CC stretch or bond length alternation. The three modes actually are the essential, the major contribution to the reaction coordinate, and these are the modes which control the fate of the molecule when it reaches this conical intersection region. And as Massimo explained yesterday, based on ensemble of trajectories which can be computed, if you compute such an ensemble of trajectories, you may compute, so here is represented the torsion around the double bond as a function of time. You may compute a distribution of decay events, decay times, and you may compute whether each molecule would decay towards forming the photoproduct or back towards reforming the reactants. And this branching ratio can be evaluated, and it is shown to be highly correlated with the very motion of one specific vibrational mode at the moment of decay. So this delta angle is the difference between torsion and hoop. So it means that whether the hoop is decaying, reducing, or increasing, this will decide what will be the fate of the molecule. So the important conclusion of this work here is that the relative phase of a few critical vibrational modes control the photoisomerization quantum yield in this photoreaction. The question that has been raised also by Massimo Liucci for some time already is, can we possibly engineer such an efficient photoreaction, photoisomerization in a synthetic compound? And possibly, can we improve the quantum yield of molecular switches and molecular motors just by learning from what happens in the protein with retina? So this is, here I show the example of biomimetic, so-called biomimetic switches, the pi electron system of which is mimicking that of retinal in rhodopsin with a characteristic charge transfer character in the first excited state. And this very molecule has been shown by us indeed to reproduce a similar vibrationally coherent photoreaction as the one observed in retinal in rhodopsin. But the quantum yield is still only 21% for this molecule. The next question is, can we also engineer, based on this biomimetic design, can we engineer molecules which would rotate always in the same direction? So can we design molecular rotary motors which would have biomimetic, which would be inspired by retinal? And so here, a first theoretical work that was done several years ago already was simply showing that by inserting here a chiral center here next to the double bond, that would be enough in this small reduced model. That would be enough to engineer, to impose unidirectionality. Since then, there is another family of biomimetic molecules which have been designed also by Massimo Liucci and Marco Paolino. This molecule, instead of being a cation as the first one, is now an anion, but the pi-electron system is still very similar, and there is a very similar charge transfer character in the first excited state. So it undergoes a similar photoreaction. This one is chiral here, so we believe it is a rotary motor, but we still have not been able to prove experimentally the directionality of this molecule. And recently also a new family of rotary motors have been designed by the group of Ben Feringa, which turn out to have a very similar structure as this biomimetic compound. This one has been demonstrated to be a real 4-stroke motor, and it is approaching the electronic structure of these biomimetic compounds with this methoxy group having some electron donating properties which tune the electronic structure close to that of these biomimetic compounds. So the fact is, actually, this motor has only a quantum yield of 10%. So we have been able to design electronic structures which reproduce a part of the outstanding properties of the photoisomerization of rhodopsin, the vibrational coherence, but still the quantum yield is optimizing the quantum yield appears out of reach. And so this question remains. So based on the discussion on the relative phase of vibrational modes in rhodopsin, as an experimentalist, we would like to be able to visualize the nuclear motions while the molecule undergoes the photoreaction and try to possibly monitor what would be the phase of the relative phase of various modes involved in the photoreaction. So several years ago, we developed in Strasbourg this so-called vibrational coherence spectroscopy. So this is not a new technique. We are not the first one to develop this. It has been developed over the years in various implementations. There are various possible implementations of this vibrational coherence spectroscopy. Some of them have been developed and pioneered to study the photoreaction of rhodopsin itself. And here we implement it in a very simple way. We do a standard pump probe experiment, but we use a very short pulse, below 10 femtoseconds. And when you do that, when you excite essentially any molecule with a very short pulse, then you trigger vibrational wave packets, and you can follow how these vibrations, so you can monitor signatures in form of oscillations like this, signatures of the vibrational motions, and you can follow how these motions are guided by the potential energy surface as a function of time while the photoreaction proceeds. So if you take actually a Fourier transformation of these signals, you recover the Raman signatures of the mode which are activated by the transition and activated along the photoreaction. And so this vibrational coherence spectroscopy is actually nothing but the Raman spectroscopy that we perform in the time domain. Using this experimental approach, we have been able to demonstrate that this biomimetic switch that I introduced earlier is indeed reproducing a photoreaction similar to that of rhodopsin. And we were able to show that a key ingredient to reproduce this vibrationally coherent photoreaction is to have here this methyl group, which causes some strain, some steric interaction with this part of the molecule, such that the molecule is pre-twisted in the ground state, and only this pre-twisted molecule has a very fast and vibrationally coherent photoreaction, which is represented here by this scheme. Whereas if you consider now the same molecule without the methyl group, then the ground state structure is very flat, and we can excite and detect signatures of vibrational coherence, but they are observed only in the excited state. The excited state lifetime is a bit longer, and the vibrational coherence disappears before the molecule reaches and crosses the conical intersection. So this has been published a few years ago as a design strategy to engineer the vibrational coherence in this kind of biomimetic compounds. Okay, and now what we are working on, so now is so to say the second part of my talk, which is to describe our new experimental developments. We are upgrading, so to say, this pump probe experiment with very short pumpers into a two-dimensional spectroscopy setup. And to do so, there are several ways to implement two-dimensional spectroscopy, but the strategy we choose is to simply convert this pump probe experiment into a similar pump probe experiment, but instead of one pumpers, we use now two pump pulses, and we control the time delay tau between these two pump pulses. So instead of recording transient absorption as a function as the probe wavelengths and as a function of time delay between pump and probe, we now have an additional time delay. The transient absorption depends on this time delay between the two pulses, which we scan. So we have two time constants that we have to scan in this experiment. So the experiment takes significantly more time. And then we use the principle of Fourier transform spectroscopy. So we process the data by Fourier transformation along this tau time constant. And this provides the transient absorption as a function of the excitation wavelength. So here now we see that the signal, transient absorption signal, which is still resolved in time as a function of time delay between excitation and probe, is now a two-dimensional spectrum because it is resolved as a function of a probe or detection wavelengths and excitation wavelengths. So what we hope to learn with that is how we will be able to resolve the coherent dynamics of these molecules as a function of excitation wavelengths, meaning as a function of the initial potential energy. So depending on what is, we use very broadband excitation pulses, so we will be able to resolve the kinetics as a function of this pump wavelengths. And possibly we hope to see whether the oscillations, the nuclear motions, and possibly the phase of these nuclear motions depend on the excitation wavelengths, and later maybe depend on the chemical design of the compounds as well. Okay, so now I go into the technical part of the talk. I'm simply describing how we built this experimental setup. So first, we need to produce a pulse pair of blue UV light with interferometric stability, because since we want to take the Fourier transformation, we need to have interferometric stability between the two pulses. So the first step is to produce one single pulse to start with, which is a very short pulse, which is in our case 7 femtoseconds, and which is here still in the visible to near infrared range. And we use a conventional strategy, which is to inject a hollow core fiber, which is filled with argon gas. And so to inject it with a conventional 800 nanometer 40 femtosecond pulse, we will have nonlinear propagation through the fiber, which will broaden significantly the spectrum. And then with so-called chirp mirrors, we can recompress temporally this pulse down to 7 femtoseconds. So then we have to make a pair of such pulses. And to do so, we use the so-called twins device, which has been designed and demonstrated in the group of Giulio Cerullo. This is a clever implementation of birefringent plates and prisms, which are cut with different orientations of the optical axis, which enable to delay one pulse propagating along with one polarization with respect to a second pulse propagating with the orthogonal polarization. And so by simply displacing with a motorized stage, inserting more or less of this pair of prisms, we can control very accurately the time delay between the two output pulses. So here at this stage, we have two pulses which are still visible to near infrared, and we perform the sum frequency generation of this pulse pair with a very long pulse, which is simply obtained by spectrally filtering now with only 1 nanometer interferometric filter, the initial pulse. And so we have this very broad pulse, and we can simply engineer the sum frequency between this one and the pulse pair. And this is how we generate this blue pulse pair. So here is the spectrum of the pulse at the output of the hollow core fiber. And here is the blue spectrum that we can generate. So we have some tunability between about 350 nanometers and 430 nanometers. We can tune a bit this blue pulse, which is typically 4,000 wave numbers broad. We can tune it a bit depending on the phase matching condition here for the sum frequency generation. And we can demonstrate if we inject this pulse pair into a spectrograph, we can monitor what is called spectral interferometry, and we can monitor the spectrum of these pulse pairs as a function of the time delay between the two, and we resolve it as a function of pump wavelengths. So if we integrate along the time delay, we have the measurement of the pulse spectrum. And if we now integrate along the pump wavelengths, then we have the autocorrelation trace of the pulse. Okay, so these are technical details, but this demonstrates that we are indeed able to produce this pair of interferometrically stable blue pulses, which is actually not so common. There are 2D experimental setups around in the world, but there are none which have been designed with at such excitation wavelengths around 350, 400. Okay, so the next step is now to use this pulse pair as a pump to excite molecules in solution. And so the rest of the experiment is the same as what we did in the previous pump probe experiment. We use a probe, which is actually a white light generated by in calcium fluoride. So this is a super continuum of white light, which contains all probing wavelengths from the UV to the near infrared, and we can control accurately the delay between all the three pulses. We have a reference beam to have a better signal-to-noise ratio and sensitivity. And here now we have, I'm just demonstrated this experiment. So these are the very first data that we collect with this two-dimensional setup. So we did some experimental demonstration on perylene. So perylene is not isomerizing. It is fluorophore. There is no photochemistry here. It's just to demonstrate the experimental facility. So this is the absorption spectrum of perylene in red, and in blue the pump spectrum. And here are the typical two-dimensional maps that we are now able to record. So this is for the time delay between excitation and probe of 20 picoseconds. And you see indeed that we have a spectrum which is resolved as a function of probe wavelengths, but also as a function of excitation wavelengths. So this data is the raw data which has been processed by Fourier transformation along this tau delay. So it is known that if you integrate along the excitation wavelengths such map, you should recover the transient absorption spectrum for the same time delay that you would expect in a conventional pump probe experiment. And this is what we observe. We see here a negative signal, which is the ground state bleach of this molecule. We have stimulated emission, which also is characterized by the similar vibrational progression, and we have some excited state absorption here. And you see that there is also some structure now along the excitation wavelength. So we can also characterize this structure that we have in the signal, which is nothing but the excitation probability of the molecule as a function of excitation wavelength. So this structure that we have across the map is actually the overlap between the absorption spectrum and the pulse spectrum. So the fact that we have a very structured pulse and a structured absorption spectrum for the molecule directly causes this structure in this direction. Okay, so now I can vary continuously, stepwise, the time delay between excitation and probe, and I can produce this kind of movie where you can see, for instance, if we do the experiment on the solvent alone, we see what is called the solvent artifact. So this is some signal which is generated by the interaction between pump and probe in the solvent, which is due to the fact that we use a very broadband chirped probe pulse. But we also see that the signal of the molecule is showing up around time zero. And if we continue the movie, you will see here that there are very pronounced oscillation left and right of these stimulated emission signal. So this is the signature of a wave packet in the excited state, which is oscillating back and forth around some equilibrium position in the excited state. So we can, next slide. I can now study in some more detail for one of these maps. I can look at, so the full set of data would be actually a cube, a pile of such maps as a function of the time delay between excitation and probe, and I can plot the evolution of the signal as a function of time. So here what I do is I integrate again along the excitation axis along this white line, and this is reproducing the pump probe signal that we would have at in this example 468 nanometer probe wavelengths, and we would see, and we do see actually when we do the experiment independently, the conventional pump probe experiment, we record exactly this data. This is the oscillation that we have in the conventional pump probe, because there are some wave packets which are created in the excited state of this perylene molecule. But now if I look at the same time dependence without integrating along the excitation wavelengths, but resolving at these very white dots at specific excitation wavelengths, here is what I find. We monitor actually, so this is remarkable. We have more pronounced oscillations. So the contrast of these oscillations is more pronounced. So this is a more sensitive way of detecting vibrational coherences. And we see that the phase of these oscillations is not the same. It depends on the excitation wavelengths. For instance, you see that these yellow and brown curves are almost out of phase. And this is why when you integrate the signal along the excitation wavelengths, the average signal is actually has a lower contrast, because you have partial destructive summation of these non-phased oscillations. So this is presently the status in our lab. This is the very recent data. So we are very excited that indeed with this 2D experimental setup, we can detect with enhanced contrast pronounced signatures of vibrational quotients. The phase of these vibrational quotients is not something we can yet discuss about. It is not yet clear whether we learn something new in this pyrroline molecule by analyzing how the phase depends on the excitation wavelengths, or whether we may learn something about the residual spectral phase of our pump laser. So there may be some more experimental things to analyze, but if I'm now concluding, and if there are two message you may remember from this talk is first message, at conical intersection, the vibrational motions control the photoreaction quantum yields, and what is more, the relative phase of vibrational motions is central at defining this quantum yield. And in our lab, we have been developing this blue UV excitation, broadband UVV detection 2D spectroscopy setup, which allows us to monitor vibrational coherence with outstanding contrast. And we do detect that we can characterize the phase of these vibrational motions as a function of the excitation wavelength. So next step would be to apply this experiment on molecular switches and possibly detect the relative phase of different vibrational modes as a function of the excitation wavelengths. And this is it. I thank you for your attention.